Hello, my name is Hyungsuk Lim, and today I'm going to talk about risk analysis of multi-level complex systems and an application to regional risk analysis of interdependent engineering economic systems. The economic impacts of natural hazards depend on damage to buildings and infrastructure and their loss of functionality. The physical state and functionality of engineering systems impact regional economies. Damage to engineering systems and their cascading loss of functionality causes the initial economic shock due to losses in physical assets and service disruption. The recovery of engineering systems following the initial economic shock is also critical for re-establishing economic stability. Quantifying uncertainties in predicting both initial economic shock and recovery is crucial toward reducing those uncertainties and enhancing overall resilience. So to effectively understand and mitigate the economic impacts, it is crucial to integrate engineering and economic systems and capture uncertainty in disruptions and how they propagate within and across these systems. So why existing regional risk analysis tools fall short? First, there is a lack of integration between engineering and economic systems. Engineering research has mainly focused on modeling hazard and their impacts on interdependent engineering systems, considering economic consequences in terms of direct damage cost. Economic research has focused on adapting general macroeconomic models to capture potential shocks within economic systems posed by hazard. And quantifying uncertainties in predicting impacts on regional economies has not been accounted. This process includes the propagation of uncertainties from hazards through to damage and functionality assessment of engineering systems and economic systems. So we develop a multi-level probabilistic computational workflow for regional risk analysis of interdependent engineering economic systems. The computational workflow captures the full chain of interdependent engineering economic systems consisting of hazard analysis, damage to interdependent engineering systems and their loss of functionality and subsequent recovery, and the initial economic shock and post-disaster economic recovery alongside the physical state and functionality of engineering systems. By propagating uncertainties throughout the workflow, we quantify uncertainties in predicting the initial economic shock and post-disaster economic recovery. We then identify main sources of uncertainty that significantly influence both the initial economic shock and post-disaster economic recovery using global sensitivity analysis. So here's the outline. First, we are going to discuss the multi-level probabilistic computational workflow for interdependent engineering economic systems. And then we will discuss an example of the developed computational workflow. The multi-level probabilistic computational workflow for regional risk analysis consists of three phases: mathematical representation, immediate impacts of hazard, and post-disaster recovery. And in the figure, the left column shows the system's actual state, the middle column shows the input-output data of the computational workflow, and the right column shows the functional relationships among the submodels. We also categorize three general sources of uncertainty, which are sample error, E1, uncertain input, E2, and model error, E3. In the next three slides, we discuss the three phases in detail. First, in the mathematical representation phase, we model the pre-disaster states of engineering and economic systems and natural hazards. Using a broad range of building types and infrastructure components, we model the pre-disaster states of engineering systems. To model economic systems, we use quantitative economic data such as flows of wedges, capital income, and investment. We model the hazard using available observational data. So for example, ground motion prediction equations relate seismic characteristics such as earthquake magnitude and fault types. Next, to capture the immediate impacts of hazard, we model the initial economic shock, considering physical damage to engineering systems and their loss of functionality. We predict physical damage to engineering systems using fragility functions. And for linear infrastructure components, such as water pipelines, we use repair rate functions instead. And we then predict their loss of functionality by modeling engineering systems as networks. And based on the physical damage to engineering systems and their loss of functionality, we quantify the initial economic shock. And during the post-disaster recovery phase, we model the economy recovery alongside the recovery of engineering systems. We model the recovery of engineering systems as the duration required for damaged system to reach their intact state. Incorporating the recovery of engineering systems and their repair cost, we quantify the recovery of economic systems. And here we use a computable general equilibrium, in short CGE, model to quantify the impacts on regional economies. The CG model represents regional economies by capturing complex interactions among industries, including relationships between price and the supply and demand of commodities. CG analysis is a quantitative methodology in regional economic modeling for impact and policy analysis. The CG model represents the simultaneous optimized behaviors and interactions between economic agents, which are household, firms, and local government. Capital stock and productivity are key parameters to quantify impacts on regional economies in the CG model. So first, we quantify the initial economic shock by accounting for damage to engineering systems. Here we consider capital stock loss to quantify the initial economic shock resulting from damage to engineering systems. We use the appraisal values of engineering systems to quantify their capital stock loss. We also include essential components in infrastructure, such as power generators, transformers, and substations in power infrastructure, and booster pumps, pumping stations, tanks, and pipelines in potable water infrastructure. We also account for the functionality loss of engineering systems. Infrastructure provide essential services to other industries for production, such as power and water. And essential services affect how efficiently industries transform inputs into outputs. Service disruptions due to the loss of infrastructure functionality reduce this efficiency. And such efficiency is captured by productivity in the CG model. We model the reduction in the productivity to capture service disruptions. As the services provided by different types of infrastructure are not substitutable, the minimum functionality among infrastructure governs the productivity. We also quantify the post-disaster economy recovery by incorporating the restoration of engineering systems, including associated repair cost. The total repair cost is categorized into the Federal Repair Fund, local repair cost, and insurance, reflecting the respective entities responsible for payment. So for example, in the US, FEMA approves the Federal Repair Fund for the region subjected to hazard. For commercial buildings, the local repair cost is paid by local industries. For public infrastructure, the local repair cost is paid by local government. The repair cost affects time-dependent capital stock recovery and economic supply-demand equilibrium in the region of interest. Throughout the workflow, we use a formulation for the uncertainty propagation to quantify uncertainties in predicting economic impacts and identify the main sources of uncertainty. Tabande et al. Developed a multi-level uncertainty propagation approach to reduce the problem dimensionality and a variable groupings approach to reduce the number of model evaluations in the regional risk analysis. The idea of a multi-level uncertainty propagation is to use the hierarchical structure of the computational workflow to express it in the form of function compositions and then perform sensitivity analysis for nested functions. The idea of a variables grouping is to reduce the number of simulations for sensitivity analysis. So far, we've discussed theoretical part of the multi-level probabilistic computational workflow, and let's move on an example of the developed computational workflow. Here, we implemented the developed workflow on Shelby County, Tennessee. The example considers 300,000 residential and commercial buildings and power and potable water infrastructure subject to earthquakes originating from the New Madrid seismic zone. And in the subsequent slides, we discuss the sources of uncertainty in the workflow from seismic hazards to post-disaster economy recovery, and the quantified uncertainties in predicting resilience matrix of regional economies and identified the main sources of uncertainty. First, we consider the spatial variability and uncertainties in seismic hazards by generating a pool of ground motion intensity maps. Based on the characteristics of the New Madrid seismic zone, the generated maps represent full range of earthquake scenarios, from frequent small events to rare large events. The uncertainties in the generated maps are location of epicenter within seismic zones, soil properties of the region of interest, and seismic event characteristics. Next, we consider uncertainties in predicting damage to interdependent engineering systems and their loss of functionality and subsequent recovery. The uncertainties in immediate impacts on engineering systems are capacity and demand models and hazard intensity of fragility and repair rate functions. Following Sharma et al., the uncertainties in the post-disaster recovery are productivity rate of workers, working hours, and repair time. Next, we consider uncertainties in predicting the initial economic shock and post-disaster economy recovery alongside the physical state and functionality of engineering systems. We translate damage to engineering systems and the cascading loss of functionality into reduced capital stock and productivity. The post-disaster economy recovery is predicted by incorporating the recovery of engineering systems and their repair cost. The uncertainties in the CG model are the physical state and functionality of engineering systems, repair cost, and model error in predicting economic indicators. The result show the level of uncertainty in predicting resilience of regional economies and the main sources of uncertainty. Following the PDF of resilience matrix of regional economies, accounting for infrastructure increases the recovery time and uncertainty because service disruptions due to the loss of infrastructure functionality results in significant impacts on the resilience of regional economies. And also based on sensitivity indices, the groups of the damage and recovery functions of buildings and water pumps are the main sources of uncertainty. This is because buildings and water pumps contribute most to capital stock and productivity respectively. Also, we can observe that CG model error and hazard intensity are another main sources of uncertainty. So here is the conclusion. We developed a multi-level probabilistic computational workflow for regional risk analysis of interdependent engineering economic systems. The computational workflow quantifies impacts on regional economies, propagating uncertainties from hazard to post-disaster economic recovery. And as an example, we implemented the development workflow on Shelby County, Tennessee. And in this example, we quantified the level of uncertainties in the predicted economic outcomes and identified the main sources of uncertainty. As a future work, we can apply the developed workflow to other hazards, such as hurricanes and wildfires, and also other regions. Because depending on the types of hazards and regions, the main sources of uncertainty may vary. Also, we can incorporate additional socioeconomic behaviors, such as migration and workforce change, into economic systems. This is because these behaviors influence both the uncertainty in the initial economic shock and post-disaster economic recovery. Thank you for watching, and here are the list of email for authors. Thank you.